and we can begin 1.4. So the last thing I mentioned was the definition of the inverse. So we said that a matrix B would be invertible if you can find, if there exists another matrix of the same size B, so that when you multiply A and B in this order, or BA in this order, you get the identity matrix. So if such a matrix B exists, you would say that A is invertible, and then B is the inverse of A. And then because this definition is perfectly symmetric, you can also say that A is the inverse of B. So generally A and B would be, in this case, inverses of each other. And if such matrix B does not exist, if it is impossible for us to find a matrix so that when you multiply by A you get I, then we would say that I is singular. And I gave you a formula for the inverse of a 2 by 2 matrix. So we said that if A is a 2 by 2 matrix, A, B, C, D, then you can calculate this quantity, AD minus BC, which, as we will learn later, is called the determinant of A. And if that determinant is not 0, so as long as this is not 0, then A inverse would be 1 over AD minus BC times DA. You swap the elements on the main diagonal and you negate the ones off the main diagonal. Okay. So the next theorem is a square matrix with a row or column of zeros is singular. So if I give you a matrix that has a row of zeros, so for example, you have 2, -1, 3, 0, 0, 0, 4, 1, 5, something like that. Yes. The fact that it has a row of zeros, or in case if you have a matrix with a column of zeros, will make this matrix singular. Now the reason that's the case is, so imagine you have a matrix A that has a row of zeros. Then let's assume that such matrix B exists, so that AB is equal I. Then that it means that I can partition the matrix A by the rows. I will have the first row of A, the second row of A, and at some point I will have a row of zeros, and then the last row of A. So let's say A is n by n. Times B. Because if you remember, we talked about this before, partitioning matrices. When you multiply two matrices, you can partition the first matrix by the rows, you can partition the second matrix by the columns. And then that would be equal A1 times B, A2 times B, that row of zeros times B, all the way to the last row of A times B. And we know that the zero matrix times any matrix is going to give you 0. Yes, the zero matrix times any matrix is going to give you 0. So for that reason, this row will be a row of zeros. Then automatically this cannot be I, because the identity matrix that is n by n cannot have a row of zeros. We know that identity matrix that's, for example, 3 by 3 is this one. It has 3 leading ones and it doesn't have a row of zeros. However, if A has a row of zeros, then for any matrix B, AB is going to have a row of zeros, so that AB can never be the identity matrix. In other words, it's impossible to find a B so that AB is I. So that's the reason why if you have a row of zeros, then it is automatically a singular matrix. And you can do the same thing for columns. So if A has a column of zeros, as I'm showing you here, then if you assume that such matrix exists, so that BA is I, then BA would be B times, you can partition A by the columns, then that would be BA1 and then BA2 for the second column, BA3 for the third column. And then at some point, you will have to have B times 0. You will have a column of zeros. And that column of zeros ensures that this can never be I, because the identity matrix does not have a column of zeros. So if a matrix has a row of zeros or a column of zeros, then automatically it is singular. Do we understand the theorem? Any questions? Okay, next theorem. The inverse is unique. That is, if B and C are both inverses of matrix A, then B and C are the same thing. So this theorem is basically saying that it's impossible to find two different inverses for the same matrix. So if you have a matrix A and you find two inverses for that, that is, you find, for example, B, so that AB and BA is I, and you also find a matrix C, so that AC and CA is I, then this will imply that B and C are the same matrix. So in other words, you can say that the inverse is unique. And since the inverse is unique, we can have a certain notation for that. We can say that unique inverse we can denote with A to the power of -1, A inverse. Yes. So how do we prove this? That's a very simple proof. So assume that you have the matrix B and the matrix C, so that AB and BA is I, AC and CA is also I. So assume that both of these equations you have. Now, so since B is the inverse of A, then we know that BA is I. Now we multiply both sides of this by C. So we know that BA is I. We multiply both sides of this by C. That means CBA is going to be CI. However, we also have I have to multiply this by C on the other side. So CIC. However, we also know that AC is I. So let me just do that again. Forget about this. We have BA is I. We multiply both sides by C on the right. So that means BAC is IC. So that's completely logical. If I have an equation, I can multiply both sides of that equation by the same matrix and the equation still holds. Now, since C is also an inverse of A, we have AC is I. So this gives me BI, because this would be I, is equal IC. But we know the identity matrix times any matrix would be the same matrix. So that means B equals C. So it's impossible to find two different inverses for the same matrix. The inverse is unique. Make sense? Any questions? So from now on, we say the inverse of a matrix A, and we denote that by A inverse. Just as A times A to -1 is 1, and A to -1 times A is 1 for real numbers, for the inverse matrix A, we will have A times A inverse is the identity matrix, and A inverse times A is also the identity matrix. So whenever you see this, you can just simplify that to I. Any questions? Okay, theorem. The theorem that I have already explained. If you have a 2 by 2 matrix, A, which is A, B, C, D, then it would be invertible if and only if AD minus BC is not 0. So if you have this condition, then it is invertible. If you don't have this condition, then it's singular. And if this determinant is not 0, then the inverse is 1 over that non-zero determinant times d a minus b minus c. So find the inverse of these matrices. You can just use the formula to find the inverse. This one is invertible because 2 times 6 is 12. 12 minus 5, that's 7. So the determinant is not 0, making this invertible. However, this one here, if you multiply -1 and 6, you get 6. If you multiply 2 and 3, you get 6. So the determinant of this matrix would be 6 minus 6, 0. So this matrix here is not invertible. So you would just write singular. It doesn't have an inverse. Make sense? Okay, so this actually gives us another way of solving a linear system. As long as that linear system is a square system and the matrix of coefficients is invertible, we can use this method. So here we have the parametric example. I'm going to give you a concrete example with numbers. So imagine you have 2x plus 3y is equal to, and you have, let's say, 4x minus 5y is equal 3, and you want to solve this system. Okay. So we know that we can write this system as a matrix equation where you can use the coefficients, which are 2, 3, 4, minus 5. You can use X as the column matrix of unknowns, and you can use B as the column matrix of the constants. Then this linear system over here can be written as AX is equal to B. So we talked about this in 103. That was actually the motivation behind the way we define the matrix multiplication. We define matrix multiplication so that this system can be written as a matrix equation like this. Now, imagine that A inverse exists. If A is an invertible matrix, and in this case it is, because if I multiply 2 and -5, that gives me -10. -10 minus the product of these two. So -10 minus 12, that's -22. So A inverse actually exists for this matrix of coefficients. Then what can I do with this A inverse? I can multiply both sides of this equation by A inverse from the left. So I will have A inverse times A times X is A inverse times B. And then because of the properties of A inverse, this here will be I. So I have Ix is equal A inverse B, but I is like a 1, so that gives us X is A inverse B. That actually solves the system. I will get X. I have isolated X then. So this is going to be what? 1 over 22, because the determinant is 22, or -22. -10 minus 12, -22. So it's 1 over negative 22 or negative 1 over 22. I swap the 2 and the negative 5. So negative 5 goes here, 2 goes here, negative 3, negative 4. That's A inverse. So X is going to be negative 1 over 22 times negative 5, 2, negative 3, negative 4 times whatever B is, 2, 3. So that would be xy. Yeah. So if I just do this operation here, I get x and I get y. I have solved the system. So let me do that. I get negative 1 over 22. Here, minus 10 minus 9. So that's minus 19. And then minus 8 plus 6. That's minus 2. So x is 19 over 22. And y is going to be 2 over 22. So that's another way of solving a linear system, which will work for any square linear system as long as A inverse exists. It works for a 3 by 3 one, for a 4 by 4 one. We still don't have a formula for A inverse for a 3 by 3 or 4 by 4. However, the concept works. The unknown x is going to be simply A inverse times B. Does that make sense? Any questions? So in general, if you have something like this, let's say ax plus by is equal, let's say, c over, let me just use the one that's indices like this. So if you have a11x plus a12y is equal b1, and you have a21x plus a22y is equal b2, you can write this linear system of two equations and two unknowns. You can write it as a11, a12, a21, a22 times xy is equal b1, b2. So this here is A. It's called the matrix of coefficients. This here would be X. It's the column matrix of unknowns. And this here is B. It's the column matrix of constants. So the linear system can be written in very shorthand notation like this. At this point, if the determinant of this matrix is not 0, that is, if a11, a22 minus a12 times a21, if that determinant, if that is not 0, then the inverse exists. Then A inverse exists, and you can use that to get X isolated. So you multiply by A inverse on both sides, and that will give you I times X, which is just X. It's going to be A inverse B. So that would be a method of solving any 2 by 2 linear system, or 3 by 3 or 4 by 4, as long as the inverse of the coefficient matrix exists. Here you have another example like that. Like the one I just gave. Any questions? Okay. The next theorem. If A and B are invertible matrices of the same size, then so is their product. So if A and B, both of them are invertible square matrices, then A times B is also an invertible matrix, and the inverse of A times B, the inverse of that, can be proved to be B inverse times A inverse. And you can actually extend this into three matrices. If you have three matrices A, B, and C, and all of them are invertible, in other words, if A inverse, B inverse, C inverse, if all of them exist, then the product ABC is also going to be invertible, and the inverse is going to be C inverse times B inverse times A inverse. Same is true for four matrices. So if A and B and C and D are all invertible, then the product ABCD is invertible, and the inverse is going to be D inverse times C inverse times B inverse times A inverse. So the inverse would be the product of the matrices in the product of the inverses in reverse order. The proof is very easy. How do you prove that two matrices are inverses of each other? So you want to prove that. How do we prove that A and B are inverses of each other? You have to verify that A times B is I and B times A is also I. That's how you prove that. So if I want to prove that the inverse of if I want to prove that the inverse of AB is B inverse A inverse, I would have to show that this times this in any order is I. Yes? And it's very easy to prove, because if I multiply AB by B inverse A inverse, this is going to be I. So I get A inverse. This is just A. So I get A times A inverse, which is I. I can also do it in the other order, B inverse times A inverse times AB. This middle thing is going to be I. So I have B inverse times IB. This part is going to be just B. So I have B inverse times B, which is going to be I. Make sense? So again, if you want to prove this, that a certain matrix, let's say I'm going to call that D. I want to use different letters to get this idea across. If I want to prove that D inverse is, let's say, M. How do I do that? I want to prove that D inverse is M. If the inverse of D is M, that means D times M and M times D should be I. That's how I prove that. So in this particular case, I'm trying to prove that AB inverse is B inverse A inverse. So I would have to show that AB times B inverse A inverse, and the other order, A inverse B inverse A inverse times AB, is both equal I. And it's very easy to prove these two. Make sense? So we have this note, a product of invertible matrices in invertible, and the inverse of the product is the product of the inverses in reverse order. However, if you have a product of the matrices, let's say A, B, C, D, and just one of them is singular, then the whole thing will become singular. So if you have a product of 4 matrices, and out of these 4 matrices, just one is singular. So imagine that C inverse does not exist. Then the inverse of the whole product would not exist. Okay, so next example, verify the result using these 2 matrices. I'm going to give you some time to verify this. That will also give you some opportunity to practice the formula. This one, A, B, C, D. Then A inverse would be 1 over AD minus BC times D minus B minus C A. Yes. So if you look at this matrix here, the determinant is 3 minus 2, 1. So this is invertible. When you look at this one, the determinant is 6 minus 4, which is 2. So this one is also invertible. That means, according to this theorem, AB must also be invertible. And the inverse of that must be B inverse times A inverse. So this is what I want you to do. Find A inverse, find B inverse, find the product B inverse, A inverse. So you have found the left side of the equation. Sorry, the right side of the equation. Then I want you to find AB, the product, and then from AB, using the formula up here, find AB inverse. That is, find the left side of the equation and then compare them. You're supposed to get the same thing. Does it make sense what I want you to do? You have A, you have B, so you're able to find A inverse and B inverse, and you're able to find this product. That would be the right side. If you multiply A and B, you're going to get a 2 by 2 matrix. Using the formula up here, you can find the inverse of that 2 by 2 matrix. And then you can compare these two. You're supposed to get the same exact matrix. So I'm going to give you 10 minutes to do that. Okay. Any problems with example 9? Did you calculate both sides of the equation? Did you verify that they're the same? No problem. Okay, then. So let's talk about the powers of a matrix. For any square matrix, we can define non-negative powers like this. If you have a matrix A to the power of 0 could be defined to be I. So any matrix that is a square raised to the power of 0 is I, where I is the identity matrix, which is similar to the definition we have for the powers of real numbers. We know that any real number other than 0, so any non-zero real number to the power of 0 is defined to be 1. So it's similar to that definition. And then if I have a matrix A, a square matrix A to the power of n, this is simply A times A n factors, so n times. So for example, A to the power of 3 would be A times A times A. Again, this is also similar to the way you define powers for real numbers. So if A is a real number, A to the power of 3 is simply A times A times A. So that's how you define non-negative integer powers. A to the power of 0 is identity. A to the power of n is A times itself n times. Now, how do we deal with negative powers? This is how you define a negative power. A to the power of negative n is defined to be the inverse of A. So this only makes sense if A is invertible, because we are assuming that A inverse exists. So A to the power of negative n is defined to be the inverse of A, that to the power of n. So for example, A to the power of negative 3 is A to negative 1, that to the power of 3, which is going to be A to negative 1 times A to negative 1 times A to negative 1. And this third part of the definition only makes sense if A is invertible. So if A is invertible, then we define negative powers like this. Now, with these three-part definition, this part is for the power 0, this one is for a positive integer power, and this part is for a negative integer power. In these three parts, we have the following laws of exponents, which are again very similar to the laws of exponents that you have for the real numbers. So we know for real numbers, if I have a to the power of n, that times a to the power of m, that's a to the power of n plus m. Same is true for matrices. A to the power of, let's say, r times a to the power of s is going to be a to the power of r plus s. Or we know for real numbers, a to the power of n, that to the power of m, is going to be a to the power of n times m. Same is true for matrices. So you have matrix to the power of r, then the whole thing to the power of s. Then this is going to be a to the power of r times s. Any questions? Next, we have this theorem about A, which is an invertible matrix, and n, which is a non-negative integer. So according to this theorem, A inverse itself is invertible, and the inverse of A inverse is simply, so the inverse of A inverse is simply A. And this does not need to be proved at all, because it's obvious that if I multiply A inverse and A, I get I. So that means that the inverse of an inverse is the original matrix. The next one is the inverse of a to the power of n. So we know that if a is invertible, for any positive integer, a to the power of n is also invertible. And the inverse of that would simply be the inverse of a to the power of n. So this actually comes directly from the theorem that I proved above, this theorem here. So for example, if I have a to the power of 3, I want to find the inverse of that. That would be a inverse times a inverse times a inverse. Yes, because it's a and a, it doesn't matter in which order I'm writing it. I'm writing in the reverse order, but you can't see that because all of them are a's. That's going to be a inverse to the power of 3. And the third part of this theorem says, if you have a scalar, a real number that's not 0, then for an invertible matrix A, Ka is also invertible. And notice that K cannot be 0 because if you multiply 0 by A, you get the 0 matrix, and the 0 matrix cannot be invertible. It has rows and columns of zeros. But as long as A is invertible and K is not 0, Ka is going to be invertible. And the inverse is 1 over K times A inverse. Again, in order to prove this, I would just need to multiply this and this and show that it's identity. So if I am able to multiply this and this, and also in the other order, if I show this is I and this one is also I, this would be proof that the inverse of Ka, the inverse of Ka is this. And I think this is obvious because K over K is 1 and A times A inverse is I. So this is going to be 1 times I, which is I. Same for this one. 1 over K times K is 1. And A inverse times A is I. So this is 1 times I, which is going to be I. Is the theorem clear? Okay, example 10. Given A, find A to negative 3 and 4A inverse. I'm going to give you some time to work on this one as well. Example 10. So you have A inverse, you have A, and you have a formula. Then A inverse is going to be 1 over AD minus BC, DA minus B minus C. So given A is 1, 2, 1, 3, calculate A to negative 3 and 4A inverse. So if you look at the previous theorem for this one, you would have to find A inverse and then raise that to the power of 3. And for this one, you can just, according to the formula, according to the theorem above, this is going to be 1 over 4A inverse. So you would have to find A inverse and then multiply that by 1 over 4. So again, I'm going to give you some time to work on this. 5 minutes. Okay, so for this problem, since the determinant of A is just 1, 3 minus 2 is 1, so the inverse is going to be 3, 1, negative 2, negative 1. Now, 4A inverse is easy because it's 1 over 4A inverse. So it's 1 over 4 times 3, negative 2, negative 1, 1. There's going to be 3 over 4, negative 1 over 2, negative 1 over 4, and 1 over 4. And in order to get A to the power of negative 3, I need to multiply A inverse by itself and then by itself again. That's going to be A inverse times A inverse times A inverse. So I have to do 3 minus 2 minus 1, 1 times 3 minus 2 minus 1, 1 times 3 minus 2 minus 1, 1. So it's going to be 3 minus 2 minus 1, 1 times, let's multiply these two. 3 times 3, 9. 9 plus 2, 11. Minus 6. Minus 2 minus 8. Minus 3 minus 1 minus 4. 2 plus 1, 3. And then I do 33 plus 8. That's 41. Minus 24 minus 6, that's minus 30. Minus 11 minus 4 minus 15. 8 plus 3, 11. So, did you get the same thing as I did?
Yes.
Okay, great. Okay, the next thing I want to talk about is the polynomial of a matrix. So, you know, a polynomial is something like this. If you have a polynomial of degree 2, quadratic polynomial, it would be something like this. That would be a polynomial of degree 2, a quadratic polynomial. And you learn in algebra that if you graph, it's going to be a parabola and all that stuff. So if I plug in a real number into this, like for example 2, I would have to do 2 to the power of 2 minus 2 times 2 minus 3, and then the result is going to be 4 minus 4 minus 3. It's going to be minus 3. So you know all that. However, I want to define polynomial of a matrix. So imagine A is a 2 by 2 matrix. What would P of A be? So that can be defined, and it is defined like this. I just replace X with A. So that's going to be A squared minus 2 times A. No problem so far. This is going to be a 2 by 2 matrix. This one is also going to be a 2 by 2 matrix. And then minus 3. How do I solve that? Because now I have a matrix minus a real number. That doesn't make sense. So what do? I put I2 here. So if, for example, A is, let's say, the same matrix that we worked with, something like that, then P of A would be A squared minus 2A minus 3 times I squared. So it's going to be 1, 2, 1, 3 times itself. 1, 2, 1, 3 minus 2 times 1, 2, 1, 3, and then minus 3 times 0, 1, 1, 0, 0, 1. Make sense? And if A is, let's say, 3 by 3, and you have the same polynomial, P of X is X squared minus 2X minus 3, and if A is a 3 by 3 matrix, then P of A would be A squared minus 2 times A minus 3 times I3. Then you would use the identity 3 by 3 matrix. So here you have the parametric definition for that. For the square matrix A, which is n by n, and the polynomial, this is the polynomial of degree m. This is how we define P of A. So you just replace all the x's with A. However, A0 would be replaced with A0 times the identity matrix. And which identity, that depends on the dimensions of A. If A is n by n, then you're going to use in. Make sense? And the last thing that I want to cover today is the transpose and the properties of the transpose. So you know what the transpose of a matrix is? We talked about that before. We said that if you have a matrix A, let's say 2, 3, 4, 5, 6, 7, then A transpose would be, if this is 2 by 3, A transpose is going to be 3 by 2, where the first column of A, the first column of A is going to be the first row of A transpose. And the second column of A is going to be the second row of A transpose. And the third column of A is going to be the third row of A transpose. In terms of definition, we can write that A transpose Ij is equal AJI. That is, the entry on the ith row and jth column of A transpose would be the entry on the jth row and ith column of A. So that's the definition of transpose, which I just wanted to review. But this theorem here is about the properties of the transpose. Part A says transpose of a transpose is the original matrix. So if you have a matrix and you transpose it and then you transpose it again, you're going to get the original matrix back. Part B says the transpose of A plus B is simply the transpose of A plus the transpose of B. Part C is for the difference. Transpose of A minus B would be the transpose of A minus the transpose of B. Then if you have a scalar K times A, the transpose of that would be just K times the transpose of A. Notice that K is a scalar, so K does not have a transpose. And the last one is the most interesting one. If you have A times B, the transpose of that is actually B transpose times A transpose. And again, you guessed it, it is true for 3 matrices as well. If you have A, B, C transpose, that's going to be C transpose times B transpose times A transpose. Or 4 or 5 matrices, same story. Here you have the proof for part B. Let's assume that A is m by n and B is also n by m. A and B do not have to be a square. Then A plus B transpose and B transpose times plus B A transpose plus B transpose, both of them are going to have the same size. And then you also need to prove that the corresponding entries are the same. So again, you want to prove this. A plus B transpose is A transpose plus B transpose. Let's assume that A is m by n, n by m, and B is also n by m. Then it's clear that A transpose is going to be M by N, and B transpose is going to be M by N. So an A plus B is going to be the same size as A and B, so N by M. So this side is going to be M by N. And this other side, A transpose plus B transpose, is going to be also M by N, because these two are both M by N. So far we have shown that the matrix on the left and the matrix on the right are the same size. So that's the first step. The second step is to show that these two matrices have the same entries in every position. So the next step would be to show that the entry on the ith row and jth column of A plus B transpose is the same as the entry on the ith row and jth column of A transpose plus B transpose. So that means I have to start here and try to work my way here, using the definitions and using the known properties of real numbers. So let's do that. So I'm trying to prove this. A plus B transpose ij. Okay, according to the definition, this would be the entry on the jth row and ith column of A plus B. That's the definition of transpose. And then according to the definition of addition, this is going to be AJI plus BJI. Then, if I use the definition of transpose again, this would be A transpose IJ plus B transpose IJ, which, according to the definition of addition, matrix addition, would be A transpose plus B transpose IJ. So I started here, I ended here. That means the two matrices A plus B transpose and A transpose plus B transpose have the same entries. Is that clear? Example 12, you have two matrices A and B, and I'm asking you to verify this. So basically, you're verifying this equation. So you would have to calculate AB, and then from AB you can calculate AB transpose. Then you calculate B transpose and A transpose, you multiply them, and you're supposed to show that this is the same as this. So it's very easy. I just leave it for you guys to do. Is it clear what example 12 is asking for? Okay. Theorem. If A is invertible, then A transpose is also invertible. And the inverse of A transpose, is simply the transpose of A inverse. So that's what theorem is saying. It's saying that if you have a matrix that is invertible, then the transpose of that matrix would also be invertible. And then the inverse of the transpose is going to be the transpose of the inverse. So how do we prove this? Just like any other example that I've given you this class, you need to show that this times this in any order is I. So we have to show that A transpose times A inverse transpose, and also A inverse transpose times A transpose, both of them are I. Okay, how do we prove that? Look, for this one, I'm going to use the fact that I'm going to use this. AB transpose is B transpose times A transpose. So this is going to be A inverse times A transpose, which is I transpose. But we know I is symmetric. Yes, so I transpose, identity transpose is the same as I. If I have this matrix 1, 0, 0, 0, 1, 0, 0, 0, 1, which is I3. Do you see that if I transpose this, I get the same thing? The first row becomes the first column, the second row becomes the second column, the third row becomes the third column, but they're identical. Same for this one. This is going to be something transpose. It's going to be A times A inverse transpose. But that is also I transpose, which is I. So this proves that the inverse of A transpose is simply the transpose of A inverse. Is this theorem clear?
Sir,
Yes?
just to be sure, when you multiply the inverse of a matrix by its initial matrix, it gives an identity matrix?
Mm-hmm.
Okay.
Yes, that's the definition. Because the definition of inverse is that we say B is the inverse of A if A times B is I and B times A is I. And then we proved that there is only one inverse for every matrix. That is, if you have a matrix B with this property and you have a matrix C with this property, that is, if you have AC is I and CA is also I, then these two are actually the same matrix. So we proved that the inverse is unique. You cannot have two different inverses for the same matrix. For that reason, we decided to have a notation for that, A inverse. So whenever you see A inverse times A, you can simplify that to I, and A inverse, A times A inverse, you can simplify that to I. Okay, so assuming that all the matrices are invertible and n by n, solve for D. So here I'm trying to isolate D. I have A, B, C transpose D times B, A transpose C is equal A, B transpose. I'm assuming that all these matrices are n by n, and I'm assuming that all these matrices are invertible. Okay, how do I isolate D? I can see that if I multiply both sides of this equation by the inverse of this on the left and the inverse of this on the right, that will solve the problem. So that's what I mean. I have to write it smaller so that I can do it. So I have A, B, C transpose D B A transpose C is equal AB transpose. I'm going to multiply both sides of this by A B C transpose inverse, A B C transpose inverse on the left, and multiply by B A transpose C inverse on the right. So B A transpose C inverse on the right. So basically, I multiplied both sides by this on the left and by this on the right. I can do that, right? And I know that I'm not imagining the existence of this matrix. That matrix exists because all these matrices are invertible. So their product would also be invertible. But if I do that, the whole thing here is going to be I, and the whole thing here is also going to be I. That will isolate D. So D is this. So D is going to be, let's see, I'm going to use the fact that the inverse of a product of the inverses in reverse order. So this is going to be C transpose inverse times B transpose times A transpose. Then I have A B transpose. Then I have C inverse A transpose inverse. And finally, I have B inverse. And the only thing that I can simplify is here. I can replace that with I. So D in the most simplified form is C inverse transpose, B inverse, B transpose, C inverse, A transpose inverse, and B inverse. So notice that I cannot, for example, simplify this. I don't have any example of, imagine that this is a B. If I have a B here and a B inverse here, I cannot simplify those two. So for example, if I have something like this, if I have A, B, A inverse, C, then I cannot simplify these two. They need to be next to each other because A inverse is the inverse of A. It's not the inverse of AB. So I would not be able to cancel these two if they're far apart from each other. But as long as they are next to each other, the multiplication of that would result into the identity. So my final answer for D would be this. Are we good?
Sir, so you don't need to write the identity matrix in the final result of D?
No,
Right.
because identity matrix is like I. It's like 1. So for example, if I have, I don't know, A, yes, I don't need to write 1 times A. I just write A.
Okay. Yeah.
Yes.
Okay.
The identity is just like a 1. If you multiply identity by a matrix from any side, you get the same matrix. Okay, I'm done with this lecture.